So last time we were together, we walked through 3 different experiments, right? Do you remember this? We walked through the dropping the magnet, talked about Faraday's experiment, and then we did the motional EMF experiment. Does that sound familiar? And towards the end of the day, we had come up with this concept, this idea that, I think there it is, that an induced current was caused by this thing that we're going to call an induced EMF, because the only way that you can have a current is to have an EMF. So the EMF has to come from somewhere. And we decided that the induced EMF was a result of either a change in magnetic field or a change in area, the area enclosed by a loop. None of this stuff works if you don't have a loop. If we look at all the pictures, so when we were dropping the magnet through the coil is a loop, right? When we were talking about Faraday's experiment, if we go back here, all of those coils are loops as well, and so that's important. And then when we talked about motional EMF, again, you have a loop of conductor that has magnetic field inside it. Okay? So in all of those cases, either the magnetic field or the area changed. And so we decided to define this thing called magnetic flux, which happens to be the product of the area times the magnetic field. And so the moral of the story is that if we want an induced EMF, we have to do what to that flux? We have to change it. A constant magnetic flux is not going to give you anything interesting, but a changing magnetic flux will give you something interesting. Just one little note here, and this is how it's written on your equation sheet. If you have a non-uniform magnetic field, then we can say that the magnetic flux, I wrote this as sub B, but I realized that in your notes in the book it actually is sub M for magnetic as opposed to B for magnetic, which is what I would usually use. But anyway, so phi sub M is equal to, it's really, we're going to take the integral of B dot dA as, okay, the magnetic field changes. We're just going to add them up over all the little pieces. That shouldn't blow your minds too much, I don't think. Is that okay with everybody? Okay. Brian, you look like you're thinking or something. I'm not sure. Allergies. Okay. I just want to make sure you're okay. Okay. So this concept here is really what's going to lead us into Faraday's law. And Faraday's law is quite important, but it's not very, it doesn't blow my mind a super whole lot. It's really just quantifying the statement that we just made. So Faraday's law says that the induced EMF is equal to the absolute value of the change in the magnetic flux over time. That should be a D, not a delta. Okay? That's it, right there. If you have a loop and you change the area of the loop, or you change the magnetic field, or you change the relationship such that the flux is changing, then you're going to have an induced EMF. Okay? If you have multiple loops, what do you think is going to happen? Anybody want to give that a guess? What's that?
It's going to be multiplied by the number of loops.
Right, exactly. It's going to be multiplied by the number of loops. So if we have multiple loops, we'll just write this down. Then the EMF is going to be equal to n, the number of loops, times the absolute value of d phi sub m dt. Life is okay? So let's try this. Let's see. Oh, I did want to show this to you first. This is a picture looking at a coil from above, so you can imagine like the loop is going like this. There's magnetic field going down this page. You can calculate the flux of the magnetic field going through this loop. It's going to be the strength of the magnetic field times the area. You take that magnetic field, you're not changing the magnetic field, you also aren't changing the area, but when I turn this, does it change the flux? In fact, it does, because the angle is different, right? So flux, it's the same idea that we talked about with electric flux, with the electric field lines. It's the number of field lines that are going through the loop. So here, I've got the same area, that's my coil just rotated. So I've got no flux because even though there's an area and there's a magnetic field, there are no field lines going through the loop itself. We'll go Nathan and then Andrew. Go ahead.
All right, say you're directing a magnetic field through a solenoid, and you had a thingy, like an object that the field's going through. And even when you turn it, all the magnetic field lines still go through the thing. Would that still have the same?
Can you make that less hypothetical and more concrete for me? I'm just having a hard time understanding what you're saying.
So like, I'm saying like if like the amount, like the distribution of magnetic field is the area where it's like defined in is less than like a certain, like say like the magnetic field is less than that object.
Less than the object, like so it's smaller.
Yeah.
So like there. Okay, so let me see if I'm. So you're saying like there's only magnetic field lines here.
Yeah.
Okay.
So if you're, so if you rotate that, would that mean that it's still the same?
So when you rotate it such that it's still the same magnetic field.
Flux going through, would that still be the same?
Yeah.
Yes,
Okay.
until you start to cut it off. Yeah,
Okay.
I think that's right. Yeah, I think I reserve the right to change my answer, but I think that is the correct answer. Andrew, was that your question also, or did you have another one?
No, but I figured it out.
You sure?
Yeah.
Okay. Brian? Okay. Okay. So what was I going to say? Generally, when we talk about it, the magnetic field isn't going to be a smaller size, like have a smaller range than the loop itself. So generally, I think we can talk about it in terms of that that cosine theta that we had there. But I think I believe that if the flux is still the same, even if you've adjusted it, then it's going to be the same flux. Yeah. Okay. All right. I'm going to give you a question to work on here. I did print this out for you to look at as well. And just so you have it, so you have to copy it all down. So it's just like a make sure that this makes sense in your head sort of thing. There we go. 1, 2, 3. You're welcome. So take a look at this, see if you can kind of conceptualize what is going on here. Imagine what's happening and then have a conversation about it with your partners.
Tesla per meter squared.
Yeah, Tesla.
You could call it a Tesla times meters, not per, times, right? So flux is B times A. So that's Tesla times meter squared. A Tesla times a meter squared. Anybody know? Anybody know? This would be a good science bowl question. Is a Weber. Marked with a WB. Capital W, little b. Can we start at the beginning?
Yes.
Just to make sure we're doing okay? All right, what'd you get for A?
0.0015.
0.0015?
Weber.
Webers? Do we all agree on that? Does anybody disagree? Besides me.
I don't know. Multiply it through by 100.
We did. That is multiplied through by 100. There's something subtle that's different there. Change in flux, right? What does the flux start out at?
That.
Oh, yeah.
And goes to what? So what is the change in flux then? The negative of that. Yeah. Negatives are going to become very important in about 4 minutes. So I just want to make sure that we're really being cognizant of that. So it should be the negative. So negative 0.0015. Yeah. Part B, to find the EMFs, that's just applying Faraday's law, the one that I just told you, right? And you got
1.5.
1.5 volts. Is that okay with everybody? And then the current was what?
1.5 amps.
It's nice that they just give you factors of 100, right? Move those zeros. All right, how much energy is dissipated in the coil? Well, that's a good question, isn't it? Ideas, thoughts? How are you going to do that?
Wasn't that like wasn't that I squared T or something similar?
Yeah, there are those things, right? Like with I's and V's and R's and stuff. Remember those? Those definitions for power?
All power was I and V.
Power was I, V, or is V squared over R.
Oh, power is energy.
Power is related to energy, isn't it?
It is energy dissipation.
Well,
No.
power is energy dissipated in a given amount of time. So you also know that that's equal to energy or work per time.
Is that E squared over I?
No, that's an R. I don't know why you can't read my... No, it was really ugly R. Yeah. So it's the EMF or the voltage squared over R. Solve that for... So you can solve that relationship for work. Work and energy is the same thing. Right, so the energy dissipated is going to be equal to the same amount of work that you have to do. Okay. And then D, were you able to get that one figured out? Or you want to talk that through a little more? Or what do you think? How are you going to do that?
Power is force times velocity.
You could do that. Do we know the velocity? No. But we have, power is force times velocity. Where does that come from, Nathan?
The definition of power.
Force times
It's work.
Work is force times distance, right? So you can look for the force by doing work divided by the distance. When is there work being done?
It's being perpendicular
energy
to
is
the...
changing.
Yeah.
Yeah, so when there's being energy being dissipated, so when the flux is actually changing. So the reason I asked that is that we need to find this distance. How in the world are you going to find that distance? What's the distance that you're applying that force on?
Times 100 loops.
We don't have to do each other.
Yeah, we know that it's 5 centimeters. I know that I have a picture.
So we do the entire perimeter.
So let's kind of talk this through. So I don't have a square loop, but I have a circular loop, which is the same kind of idea, right? So let's imagine what's going on. So let's say that this table is emanating a magnetic field upwards, okay? And it cuts off right here. If I move this loop in this space like this, do I have a change in flux?
No.
No. So there's no induced EMF, there's no current, there's nothing interesting happening. As soon as I move this like this, now what?
The flux is changing.
I'm changing flux, right? If I put it here and then I move it like this, then there's no change in flux. But as I'm moving it like this, absolutely there's a change in flux. Once I get over here, is there a change in flux? No. So really the only time when I'm going to get a change in flux is what?
As it's moving off the table.
Yeah, so from here to there. Easier with a square than a circle. Okay? How far, if this is a square, so this is almost a square, let's say this was a loop and I'm pulling it like this. How far do I have to move it? How far do I have to apply that force?
Side length of the square.
Yeah. So it's just the 5 centimeters. Does that make sense? I really want to make sure that these make sense, not just, how do I do this problem? But bigger picture, right? Because the questions aren't always going to be this question. So you want to make sure that that actually makes sense. So let me reiterate something really quickly. The change in flux happens when the loop goes from being in the magnetic field to being out of it. The EMF that's induced only happens during that time, and the resulting current is only present during that time. Once it is out of that magnetic field, there is no more current. So it happens just for a moment. It's a momentary thing. Okay? The energy dissipated is only going to be dissipated as that loop is moving. So you have a little light bulb hooked to my coil. It's only going to be lit when?
When the thing is moving from the electric flux to away from the
Not electric.
magnetic flux.
Right. Yeah, so magnetic field is going in, so life is good. As soon as it's done, no more, no life. Okay? Because there's power that is being dissipated, we know that that energy has to come from somewhere, and that comes from your work. So it takes work. If I just hold this thing here and I'm moving it like this, am I doing any work? No. The thing is, if this has magnetic field and this doesn't, now I have to do work here because there's going to be light that's given off. Okay? If there's a light bulb. Got to listen to the whole premise and then it makes sense. Yeah. Okay?
Let's don't get fluorescence.
Whoa! So weird. All right, so if you plug numbers in, do you know what the answer is? Do you need another 5 seconds? I'll give you another moment. Looks like some people still need to work. Yeah? Does that match with what other people got?
What'd
Is
you
that okay?
get?
2.25 times 10 to the negative third for part C.
Wait. Yeah, that's what I got.
Brian agrees. Critique's happy. Yeah. And then part D. What is the average force required?
I got 0.045.
Is that okay? Issues or questions with this? The concept here really is not that hard. Well, I should say the plugging in numbers process is really not that hard. The thing that's really important is to keep in mind what's going on when an EMF is being induced, right? Change in magnetic field or change in area or change in flux, so that means that the amount of flux that's going through is going down. Okay? There's one little piece that I left out in the story. Now, in your book, they talk about them as two separate things, but usually in textbooks, I see this as one deal. Nobody's really asked me about it, and maybe it's just because you're sleepy, and maybe it's because you just trust me and you think that it'll all be okay. But there are these weird absolute value signs. Like, what the heck? Why are there absolute value signs?
Yeah, I just assume there's some reason to have these off.
There have to be, yeah, some reason. We don't know what, well, I do know what the reason is. Usually when I see Faraday's law written, I see it written like this. Okay? So the opposite of N d phi dt. This negative sign is, I would suggest, the most important negative sign in all of electricity and magnetism. Perhaps the most important negative sign that you ever learned in physics. Right there. Okay? That negative sign has a law associated with it all by itself. Like that little horizontal line has a law. And the law that it has that's associated with it is Lenz's law. Okay. Lenz's law is describing a direction. That's why it's a negative sign, right? It's a negative sign. It's describing the direction of the induced current. You remember, I hope, when I dropped that bar magnet through the solenoid with the north side down that it deflected one way. And then when I dropped it with south side down, it deflected what?
The other.
The other way. So obviously, and remember the galvanometer, that was actually reading what? Current. So the current went one way when I put north down and a different way when I put south down. And it would consistently do that. So it wasn't like just, I'll just pick a random one. It was consistent. When we dealt with the motional EMF stuff, we could figure out the current very certainly. It wasn't one way or the other, I don't know. It's always going to be a certain way. Okay? And Lenz's law is what describes that direction. Okay? The rule is as follows. I'm going to write it out in words. It'll be a lot of words and it might seem kind of weird, but then we'll try it out and see how it really makes sense. So Lenz's law says that the current caused by an induced EMF travels in the direction that generates a magnetic field opposing the change in flux through the loop. Okay. Oops. The current that is caused by an induced EMF travels in the direction that generates a magnetic field opposing the change. Opposing the change to the flux. So let's look at it in terms of that motional thing, and then we'll come back and do a couple others. So as this bar is moving to the right, what's happening to the flux?
It's decreasing, right? Because that's the end of the magnetic field.
What's that?
The flux would be decreasing because that's the end of the magnetic field right there.
No, it keeps going forward. The magnetic field just keeps going.
Never mind. Then.
Yeah.
It doesn't change. I didn't see the
So the magnetic field is continuing on this way. My picture just ended. This bar moves this way. What happens to the flux in the loop? Is it getting bigger or smaller?
Oh, there it is changing.
There is
So yeah, it's
increasing.
getting
So
bigger.
Right, yeah. Remember, flux is B times A, right? B isn't changing, but A is, and if A is changing, then by golly, it's got to be changing. So the flux through this loop is getting bigger. The loop doesn't like that. The loop says, no, and I'm not trying to give it personality, but I am, because it kind of helps to understand what's going on, okay? The loop doesn't like that change. It's going to create a current that makes a magnetic field that opposes that change. We said that the current was going this way. If you have, get your right hand out real quick. If you have a current that goes this way, that's going to create a magnetic field inside the loop that goes where? Out of the page. By this moving this way, we're increasing the flux, but now I'm putting B field going the other direction. And as a result, I'm doing what to the flux? Decreasing. So I'm undoing the change that this silly bar is creating.
So is that an actual physical loop?
Yes. What do you want it to be?
Those are two wires right there.
These are bars, right, so that this thing can slide. But they're all electrically connected so that you can get your light bulb to light up. Right?
Yeah. I'm just confused because I thought flux was just like an imaginary loops. I don't know.
No. This happens in real life. Okay, let's watch it. Come here.
So it's not just like just a caption like.
This happens, right? You ready? You gonna catch stuff?
Yep.
Okay. So, is there flux through this solenoid right now?
Yeah. Well,
Not a lot. I mean, there's probably some from some magnetic field that's being created somewhere, but nothing appreciable, right? Is there flux now?
Yes.
Yes. The magnet is inside the loop, so there is flux. Is there current?
No.
No. None of you checked. What do you need to check to see?
Like movement.
well,
Look at the galvanometer. Is the galvanometer reading anything?
Is it just
No.
balanced? Because look, it's like
Why not? Why isn't it reading anything?
there's no
because
movement.
the flux isn't changing.
Right. There is flux, but there's no change in flux. When I drop this, what happened to this? Come here, you lazy bums, come here.
I can see.
You cannot get up. Change in flux, what happens? It's deflected, right? Change in flux. It's deflected. That means there's current running through this wire. The current running through this wire is trying to undo the change that is happening. Okay? Does that make sense? Okay, because now we're going to try it out a few more times and we'll see if it actually works. I find that this is something that's a little bit tricky to see, to just intuit with your brain. So I'm going to encourage you, now that you've just sat down, I'm so nice. Everybody needs to get up for yourself because I need that blood to be flowing in your brains and your body. Come get a roll of tape. There you go. There you go. You sleepy bums. Oh yes, she said it. All right. So this is not something that's made up. This is something that actually happens. Now, is this a conductive wire? No, but it's going to give you the right idea of what's happening. So in order to have any of this happening, it has to be a loop. So that's helpful. Okay? We're going to take a look at a few of these here. Here's one right here. So I've got a loop of wire, and I've got B field. I've got this permanent magnet that's moving toward the wire. Okay? As the B field moves toward the loop, so we're going to look at it from this perspective, because if you look at the other side, the tricky thing with Lenz's law, because we're going to talk about clockwise and counterclockwise currents, if I look at my side and I say it's going this way, to me that's counterclockwise, but to you that is what? Right? So we all have to look at the same side of the loop, otherwise we're going to get different answers. Okay? So we're all going to look at the loop from this way, like as the bar is going in. Okay? So the permanent magnet is moving into the loop. As it does that, what's happening to the flux? Is it increasing or decreasing?
It's increasing. Right when it gets to the loop.
Wouldn't the B field be opposingly in the other direction?
That's not what I asked. I want to know what's happening to the flux. As this thing moves toward the loop, what's happening to the flux? Let's do it one step at a time.
So it's moving to a region weaker.
Magnetic flux is B times A, right? Is the area changing? No. Is the strength of the magnetic field changing?
Yeah.
Yes. The closer you get to the magnet, the stronger the magnetic field. So is the flux changing? Is it getting stronger or weaker?
Stronger.
It's getting stronger, right? It's getting stronger into the loop. The loop doesn't like that, so the loop is going to induce a current itself, right? What direction is it going to induce a current?
It's going to induce
Wants to oppose the change.
counterclockwise.
Yeah, it's
So use your loop. That's why I gave you loops, so you could use them, right? So it doesn't like having flux going in this way, so it wants flux going the other way. It wants flux going the other way, so with your right hand, then you can tell that it's going to have a current in which direction? Counterclockwise. So it's going to be going this way, right? Does that make sense? That is Lenz's law. That negative sign comes from this. What about in this case? The flux is what? Flux is decreasing, which means that it wants more flux, right? I don't want to change. So what does that mean? It's going to be clockwise. Okay. Here's some more. So this first one, the magnet is coming in from above. It's hard to see that, that's why I'm telling you this. North pole is moving toward the coil from above the page. So for each of those 4, I want you to see if you can figure out what direction it's going. Then we'll talk about them all 4 in a second. What did you say for A?
Counterclockwise.
Did you say counterclockwise?
Yes.
So the magnetic field is getting stronger into the page, so that means we want it to come out of the page, so counterclockwise. Yeah. What about for B?
Nothing yet.
Why?
It's not going through.
Right, there is no flux. No flux the whole time, which means there's no change in flux, which means we don't have anything. All right, how about for C?
You got counterclockwise.
Counterclockwise? So this way. So let's reason that through. I just want to make sure I agree with you. So we're pulling the coil to the right, so that means that the magnetic, or the flux is, what's happening to the flux?
Decreasing.
It's going down. It wants more flux out of the page, so that means it's going to be counterclockwise. Yeah. And D? Clockwise. Who can reason that one through for me?
Since it's shrinking, the area is decreasing, so the flux is decreasing,
Uh-huh.
and the charge is going into the page.
Not the charge.
Sorry, magnetic field.
The field is going into the page.
So it would be going clockwise because it needs to go out of the page.
Because it needs more to go into the.
Yeah, it needs.
Yeah, because it wants more into the page. Yeah. And it's simple, but it's tricky, right? You have to make sure that you're double checking what you're saying.
Yeah.
And it's not just you. This happens to lots of people, so I just want to make that really clear, right? So we said this is going clockwise, again, because the flux is going down. Flux is going down into the page, so we need more into the page. Okay? One more to look at?
Will there be questions like that?
Sure.
Sure.
I mean, it wouldn't, there might be a multiple choice question like that, although that would be kind of boring because it'd be like clockwise, counterclockwise, or none, right? So I'd probably be a little bit more creative about it. They also may have a question that, like on a free response, that isn't that simple, but it may tell you, that it may be something like the Faraday's law question, and then it may say, and which way does the current go? Right? So that might just be a piece of it, but certainly, yeah. This is also another piece here. Oh, look at this one. This is fun. So now I've got a magnetic field. The magnetic field is pointing to the left, and I've got a loop that right this moment has how much flux going through it?
0.
0. It's rotating in this way. We're all going to look at this face, the face that starts facing you, because again, if we look at the other face, we're going to get it wrong. So as it's rotating from here to here, tell me about the change in flux, and as a result, which way is the current going? What's happening to the flux? It's increasing in which direction? Into the loop. So that means it wants to undo that, right? It wants to go out of the loop, so that's going to be what? Counterclockwise. Now, here's my next question. Once it gets there, it's probably not going to stop. That would be kind of boring. So it's going to keep going. Tell me about the current as it keeps turning. So if we're looking at this face again, right, it's getting bigger, so we need something going this way. But then what happens? It starts decreasing, so now it wants stuff going this way. So that's going to be clockwise. You guys are really wide awake today. What's the deal? Do you have a good excuse? You weren't all at the talk last night, so I know you weren't up late doing that. What's your excuse? Do you have one?
Homework.
Wah. Tell me about it as it's going around the rest of the way. We've only gone 180 degrees. We're going to go all 360. Keep going. Talk to me.
Yeah, it'd just be the same thing again.
Does it switch 2 more times?
Yeah, because it'd be going like this, and that would be the exact same movement again.
I mean, the loop would take backwards this time.
The loop would be backwards, but it's a uniform loop, right? Probably.
So what's it going to do? It's going to go clockwise for the first 90 degrees, then what?
That's the second one.
For the second 90 degrees? Then what?
No, I just got a question. Why would it go clockwise for the second 90? Because the B field's still pointing this way. The induced one.
Okay, friends. I don't know what I can do to make sure that you're actually all paying attention. I'm not sure because I can't like wrangle you today. So I'm going to ask. I'm going to ask for just a minute. This is all we have to do right here, okay? Okay, so let's talk this through and make sure it makes sense. So as we turn from this face, looking this way, we want B field going this way, right? Trying to undo the change so it's going to be counterclockwise. And then, Nathan, you're arguing what?
Well, you're still going to have it. You want the net to be 0 still. So I mean, it's still going to be pointing that way. But the B field's still going to be.
So the B field's going into the page. It's now used to that. It's like, that's great. I'm glad there's B field. And then what happens?
It's like
Right.
the last problem where if it shrunk, you could say like 40 through.
Once it's here, so it's gone from here to here. We're looking at this side. Once it's here, what's happening to that B field? Or what's happening to that flux?
Like instantaneously, or?
I want to know for the second 180 degrees what's happening. I don't think you've actually thought it through, and I want you to actually think it through as a group before I talk to you guys about it. Have a conversation.
If this is the way it starts.
We're looking at it from this side. Wouldn't it then be clockwise?
If you're just staring at it.
Because we're looking at it from the same side. It would be going. It'd be the electric flux would be increased at. Go this way.
What's the decision that was made?
It goes clockwise the next 90.
And then the fourth is what? So, does the current alternate? Andrew?
Yes.
It does. This is alternating current. However, and this is the thing that's really important, it's not alternating every 90 degrees. It's only alternating every 180. So every time it turns a full 180, it's just that when we started looking at it, it was halfway through one of the directions already. Does that make sense? Nathan, you look like you might have a question.
I'm still thinking.
Okay, let me know when your question comes up if you have one. Okay? All right.